Hello, I'm Lou Bloomfield and this is How Things Work. Today's topic, wheels. Wheels are on so many objects of everyday experience, from cars and bicycles to roller skates and various pieces of machinery. The question for us today really is, why wheels? What is it about wheels that makes them so useful? And the answer is going to be, or at least primarily going to be, to control friction. Not to eliminate friction altogether. Sometimes you want friction, sometimes you don't. And the wheels allow you to get rid of the parts of friction you don't want while retaining those that you do. So to understand how wheels work, we have to start by understanding what friction's all about. And to understand friction, I'm going to actually take a step backward even further to revisit support forces. When two surfaces touch each other, they start to push on each other. They push each other away so as to avoid occupying the same space at the same time. And when I'm pushing on this table right now, I'm trying to put my hand into this table surface, it pushes on me to prevent my hand from entering the surface, and my hand pushes on it to prevent it from entering the surface. There's a Newton's third law pair there of forces, and they are support forces. I'm pushing straight down on the table, and the table's pushing on me straight up. That means the table's force on me is perpendicular to its surface. So the surface is horizontal, and the support force on my hand was upward. That's perpendicular to the surface. That's a support force. Well, the fact that surfaces, when they're in contact, can exert forces perpendicular to one another is all well and good. But what about the other directions? So there's perpendicular, in this case vertical, but what about parallel to the surface? All the forces that could be exerted on my hand, not upward, but horizontally. Those forces between two surfaces, parallel to the surfaces, along the surfaces, those are all frictional forces. And if I try to scoot my hand back and forth, left, right, and I'm gripping the surface pretty tightly, this surface is preventing my hand from moving, or at least from accelerating, by way of frictional forces. So, general category, the world of frictional forces, these are forces that act parallel to surfaces when the surfaces are in contact with one another. Now, even within that idea, the frictional forces, there are several different kinds of frictional forces. And we're going to focus on the two major categories of frictional forces, what are known as static frictional forces and sliding frictional forces. Another name for sliding frictional forces is dynamic friction forces. Same idea. I give it the name sliding because we're more familiar with the notion of sliding than we are with the notion of dynamic. Okay, so to see frictional forces in action, and those two types of frictional forces, I'm going to set aside the wagon with wheels and go after the wagon with no wheels. Sorry, wagon. This wagon, without its wheels, can't move front and back or in any direction it likes on a surface without experiencing frictional forces. And if I try to pull this wagon to your right, I'm actually pulling on it a little bit, not super hard. If I pull too hard, it will begin to skid, like that. But let me pull just a bit. I really am pulling to the right. And yet the wagon is not accelerating. That means the net force on the wagon has to be zero, despite my individual force to the right. Something is pushing it to the left. Well, that something is the table. And the table is exerting a frictional force on the wagon toward your left. And that frictional force is just enough to compensate for my pull to the right. That particular frictional force, where the wagon is not actively sliding across the surface, they have the same velocities. The two surfaces, both of them, if you're on one surface looking at the other, you're saying it's not moving, and vice versa. So no relative motion. That arrangement gives rise to static frictional forces. The frictional forces of two surfaces that are trying to slide across one another, but that are not actively doing it. So when I pull to the right on this wagon, the static frictional force of the table pushes the bottom of the wagon to the left and exactly cancels my rightward force. In fact, it adjusts, that frictional force adjusts. If I pull not at all, the frictional force goes to 0. If I pull a little bit, the frictional force develops just enough to keep the wagon from moving. If I pull harder still, which I'm doing, the frictional force from the table on the wagon, static frictional force, gets a little stronger until eventually I pull too hard, up, and the frictional force gives up and the wagon begins to slide. Basically, there's a maximum that the static frictional force of the table on the wagon can reach. But below that maximum, it's adjustable. The static frictional force negotiates just the right strength to keep the surfaces from sliding. Now, if the table is exerting a frictional force on the wagon, Newton's third law says there has to be a second force involved, the reaction force, and that would be the table, the wagon exerting a static frictional force on the table. And sure enough, that's there. It affects the table. If the table were able to respond, we might be able to see the presence of that force. Generally, the table is so massive and such, we're not going to see it. But when the table stops the wagon from sliding, the wagon pushes back on the table. All right, now that force of static friction occurs, to just sort of zoom in, it occurs because the surfaces, the top of the table and the bottom of the wagon, are not perfectly smooth in sort of a mathematical sense. They have structure there. And like fingers that are sort of interwoven a little bit, the structures get caught up in each other and they don't want to move sideways, back and forth. And therefore, these two surfaces, even though the support forces keep them from occupying the same space at the same time, the frictional forces keep these microstructures, nanostructures, sub-nanostructures from sliding across each other. Up to a point, static friction has a limit beyond which the sliding begins. The structures may begin to break off, in fact, and other such things as the sliding actually takes place. Now, the strength of that static frictional force is variable from 0, which is what's happening right now, to a maximum. And if I pull harder and harder and harder up, we've found the maximum. So static friction is adjustable. The strength of the static friction depends on the two surfaces, sort of the extent to which they grip onto each other, and also on how hard the two surfaces are pressed against one another. As they push harder on one another and summon up bigger support forces, the maximum of static friction increases. So if I push the little wagon against the table harder, for example, by putting half a lead brick in it, there you go, have some big push. Now, the force of static friction, it's a lot stronger. The maximum is huge. I have to pull very hard before I get it to slide. There we go, I got it, okay? So that's static friction. Surfaces matter, the character of the surfaces matter, how hard they're pressed against one another. Actually, the peak of static friction is observed to be approximately proportional to how hard the two surfaces are pressed against one another. So increasing the weight of something that's trying to, well, in this case the wagon, increasing the weight by a factor of 2 tends to increase the maximum static friction by a factor of 2. That's useful in certain circumstances where you want that grip between the two surfaces to increase. For example, you want a vehicle. It doesn't sound like you want to have you want to have friction around with your car, but if you want your car to be able to grip the road better, which in circumstances you actually do, you can add weight to the car, press the gripping surfaces, the wheels, harder into the ground. So we'll come back to that, hopefully. Okay, that's static friction. How about sliding friction? Well, sliding friction is between two surfaces that actually are actively going across one another, and it is typically a single value, somewhat independent of how fast the vehicle is going. So let me get the brick out of there. Just going to reduce the grip here. this wagon, once I get it moving so that it is now still static friction, still static, now it's sliding friction. The force of sliding friction on that wagon, which is the force the table is exerting on the wagon towards your left, trying to fighting the relative movement, that force is pretty much a specific value. It has a certain strength. It depends on the surfaces and how hard they're pressed against one another, but not on other things like how fast the two surfaces are sliding across one another. It's pretty independent of how fast the surfaces are going. And it's not zero, and it's not an enormous number. It's some specific number in the middle. Its direction is always opposite the relative motion. So if I pull the wagon to the right, and so it's moving to the right, the frictional force, the sliding frictional force on the wagon is to your left. If I pull the wagon to the left, so it's moving to the left, now the sliding frictional force is to the right. It's always trying, in this case, because the table is motionless and very unlikely to change its velocity, it always tries to bring the wagon to the table always tries to bring the wagon to its velocity, which is zero. It's trying to stop the wagon. The wagon, on the other hand, is trying to speed up the table to move at the wagon's velocity. The table, because of everything it's connected to and its mass and all that, is just not going to do much. So sliding friction always tries to bring the two surfaces to the same velocity. If one is more willing to adjust than the other, the one that's willing to adjust, adjusts. All right, that's sliding friction. Again, if I put the lead brick back in and press the two surfaces against one another, sliding friction will again find one specific value that it loves. There it is. And it doesn't depend on how fast the wagon is going or anything. It's always opposite the wagon's relative motion on the table. And what else? It's pretty much proportional to how hard the wagon is pressed against the table. Okay, so that's static friction, sliding friction. It's going to turn out that in playing with wagon wheels, putting wheels on the wagon, we are going to do our best to get rid of sliding friction while retaining static friction. So that's where we're headed. Now, why would you do that? So to say that more carefully, the wheels on a wagon, as in this wagon, those wheels do not eliminate static friction, but they do eliminate sliding friction. There is no sliding going on as this wagon moves back and forth. And that's pretty useful. And the fact that there still is static friction going on is also pretty useful. So why? So first let's look at what's the problem with sliding friction? Why would you want to get rid of it? Well, if you think back to the sort of the microscopic picture of where does friction come from sort of the interdigitation and contact between the tiny microscopic structures on the surfaces. Well, if there's no movement, no relative motion between the two surfaces, they can sit there staring at each other and gripping each other, but nothing much is happening. If there is relative movement, these little interdigitations hit each other, and they do things to each other. For example, they break each other off. They wear each other out. So sliding friction wears the surfaces. The top of the table and the bottom of the wagon are both, as they rub, both losing stuff, or getting it, exchanging particles and atoms and molecules and causing trouble. And that's familiar from things like your shoe soles wear out from scuffing them around on the floor. Even things like the stone staircases of buildings with enough traffic and people scuffing their feet on them, sliding friction, they wear away the stone. So glaciers, I guess, wear away stone too. Anyway, sliding friction wears stuff out. The other thing it does is it wastes energy. Now, what does it mean to waste energy? By that, energy is in a conserved quantity. You can't just like destroy it. You can give it to other people and stuff, but okay, so what's the wasting part? The wasting part is that sliding friction tends to convert ordered energy, the energy that's equivalent to work and can do work, into disordered energy, fragmented, shattered energy that can be described as thermal energy. Thermal energy is energy that is chopped up into tiny little portions and given out statistically to the atoms and molecules and particles that make up materials. So thermal energy is everywhere. You don't see it directly because the microscopic motions of all the little particles are not easily detected directly. They're present. They're certainly present, and they can be detected indirectly. The most obvious way to detect that thermal energy is by way of a thermometer. You see it as temperature. But anyway, if you take lovely ordered energy, energy that can do work, and turn it into thermal energy, the disordered stuff, it is very hard to undo that conversion. Just like if you take a vase, a beautiful glass vase, it's all carefully ordered, and you smash it on the floor, it's still all there. It's just broken up into little pieces. And to get those pieces to come together and reassemble as a vase is just not going to happen. It's not the laws of motion that prevent that return to the beginning. It's a statistical issue. It's statistically so unlikely that any simple activity with those pieces of broken vase would ever have it reassemble into the original vase, that it never happens. And the same is true of thermal energy. If you take 1 joule of work and turn it into 1 joule of thermal energy, the energy's all there. Just like the glass shards of the vase were all there. But getting all those fragmented pieces of energy back together into the 1 joule of work, statistically unlikely. And by statistically unlikely, I mean like winning the lottery 1 billion times in a row. It's not going to happen, okay? Twice in a row, maybe. 1 billion times, For all practical purposes, that's never. Okay, so sliding friction turns work or ordered energy into thermal energy, disordered energy. How so? Well, let's watch it happen. If I take this little wagon and I'm going to give it some energy with my hand, I'm going to push it to the right. As it moves to the right, I'm going to give it energy. It's going to briefly have kinetic energy. You'll see it. Kinetic energy, wow, ready? And then watch what happens. It stopped. It had kinetic energy over here, and now no energy. It's not moving, so it has no kinetic energy. It's not higher than it used to be, so it has no gravitational potential energy that it didn't already have. The energy's gone. Where'd it go? Well, it's thermal energy, actually. It's the top of the table and the bottom of the wagon have both gotten a little warmer than they were before. The energy was chopped up into little pieces and is now thermal energy in those surfaces. We can also see this in terms of work. So I did work initially by pushing the wagon to the right as it moved to the right, and I gave it energy. And watch what sliding friction does. So I don't want it to bounce so much, so let me get it going. Okay? During the stopping process, the table and the wagon were pushing on one another with forces of sliding friction. The wagon was pushing the table to your right, and the table was pushing the wagon to your left. The wagon, because it definitely exerted a rightward force on the table, however, did not move. So the wagon did 0 work on the table. Okay? So no energy went from the wagon to the table by way of work. On the other hand, the table exerted a leftward frictional force on the wagon. As the wagon moved rightward, the table did negative work on the wagon and reduced its energy. So the wagon, in skidding to a stop, lost its energy. It was by way of negative work from the table, but it didn't give the table any energy. There wasn't a transfer here. The rule of the perfect transfer of work seems to have failed. That is, the table did negative work on the wagon failed to do positive work on the table. What happened? Well, the wagon actually did do little teeny pieces of positive work on the table's surface by way of sliding friction. And that chopped up the energy into little teeny sort of movements of the top surface. It would be like if I take a hairbrush and I push my fingers on it. I'm doing little bits. The hairbrush, in principle, is not moving. There. But as I push on all the little teeth of the hairbrush, bristles, I do work on each one. And it all gets chopped up into, each one got its own little dose. And that's what's happening here at the table. And so there's little movement as a result of this in the microscopic structures that are the top of the surface and the bottom of the wagon, and they get hotter. They have more thermal energy than they had before. But the energy is no longer useful. It's still here, so I scoot this over. The energy is still there, and in principle, that energy could get itself together and push on the wagon and have the wagon go back to full speed and head to the other direction, for example. But that's statistically never going to happen. So, bottom line, sliding friction wastes energy. It turns useful order energy into thermal energy. And that's why we don't have cars that scoot along the surface like that. Too much waste of energy. Things slow to a stop too easily. Furthermore, they wear out because sliding friction also causes wear. So what do? Well, the solution is get rid of the sliding friction while retaining static friction. And what I want to do is look at what happens when something rolls. If I take this it's just a jar that has a black line painted on it. If I roll this thing along, as it rolls, the surface of the bottom surface of the plastic jar and the top surface of the table, they never slide on one another. They just, the bottle here, watch that line. It lands on the surface, now it's touching, and now it lifts up. Land and leave. It's like if you take your hand and you roll your hand, your fist across your palm, there's never any sliding. It's landing and leaving. The surface comes down and then goes up. So this jar is experiencing no sliding friction because there's no relative movement between the two contacting surfaces. But there is, or certainly can be, static frictional forces. If I try to push the jar toward you or away from you, even as I'm rolling it, to an extent, I mean, if I push hard, it moves a little, but it's basically, it's got good grip toward you and away from you. It's static friction, but there's no sliding friction. And that's the beauty of a wheel. If I take this poor baby here, set it aside for another day, and pull out the wheeled wagon, in this case, the wheels do that same trick. They land and then they leave. Land and leave. Land and leave. Only static friction. And the static friction means that if I'm riding this wagon, it rolls left-right beautifully. No problem. And it wastes no energy, so that I can keep it, if I get it going, it keeps going because it's not wasting energy by sliding. But if I want to skid it toward you or away from you, that's harder. It won't skid. It's got good traction and grip. It rolls this way nicely, but toward you, away from you, no. And in fact, if I turn the wheels a bit, now it steers. So the steering is done by static friction across the wheels, preventing them from sliding left-right, while the wheels can still roll forward and backward. So you're getting the best of both worlds. You're getting no energy wasted to sliding friction along the direction of the wheel rolls, but good grip from static friction across the wheels. And that's the beauty of wheels. Wheels in a nutshell. I will sort of finish here by saying that there are two types of wheel. There are wheels that turn when the vehicle on which they're attached moves, what are called free wheels. And these are free wheels. These wheels, if I pull the wagon to the right, so if I give the wagon a rightward velocity, the wheels turn as a result of the wagon's movement. They turn because of static frictional interactions between the bottom of the wheel and the top of the table. To keep that wheel from skidding, the static friction from the table exerts a force on the bottom of the wheel. That force produces a torque on the wheel that causes the wheel to begin rotating, just right to roll. That's a free wheel. The other possibility is what's called a powered wheel. The wheels on cars, at least typically the front two wheels, or if it's a all-wheel or four-wheel drive vehicle, it's all four wheels. Those wheels turn not because the vehicle is moving and that makes the wheel roll. They turn because the engine turns them. So the engine twists that wheel with the torque. And the result is the wheel begins to rotate. And the wheel and the pavement interact with one another by way of static friction to try to stop the wheel from skidding. If the wheel didn't, if the car just sat there and the wheel rotated, the wheel would skid. It would spin like this. Right? Skid, 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 skid. So instead, the wheel and the pavement grip each other, and as the wheel tries to turn, to rotate, as forced by the engine, actually torqued by the engine, the whole vehicle begins to move to allow that wheel to roll properly so that it doesn't have to skid. It instead does the touch and release trick. It lands and leaves. So powered wheels propel the vehicle forward. The engine tries to rotate the wheel. Ultimately, it will succeed. And the pavement pushes on the wheel to prevent the wheel from skidding. And that push on the wheel, which is a horizontal push, as friction from a horizontal pavement must do, that horizontal force is the only horizontal force in the whole vehicle. It makes the vehicle accelerate. It heads forward. So, powered wheels and free wheels, sort of two ends they're the yin and yang. They're not the two ends of the same thing. Yeah. Anyway, there you have wheels trying to control friction and use it strategically. I will say that there are actually other types of friction around. For example, if you underinflate the wheels of the tires of your car, you will actually waste energy there too, and it's called rolling friction. It's not static friction or sliding friction. It is a friction that occurs because as the wheel lands on the surface, if it's underinflated, and in fact to some extent even when it is inflated, as the wheel lands, it presses against some amount of surface of the pavement, and the tire deforms and it scoots a little in and out as it lands and leaves, and it rubs by virtue of spreading. Just like if you took a ball and shoved the ball into the table, the ball has to do a little bit of scooting. Parts of the surface, some of it go this way, some of it go that way, and that scooting and unscooting of an imperfectly inflated tire can waste a fair amount of energy. Sort of little local pieces of sliding friction. And that is a reason why you want to properly inflate the tires of your car, of your bicycle, of anything that has an inflatable tire. If you underinflate it, you will waste too much energy to this third type of friction known as rolling friction. All right, with that I will stop, and that has been the story of wheels.